Hi everyone, and welcome to our first lecture for Introduction to Statistics in Criminology and Criminal Justice. This week we're going to talk about just the very basics of statistics and learning about data and how to graph data and summarize data. So we're going to start with Chapter 2 in our textbook, which if you have the physical book, we'll start on page 26 if you want to follow along. One thing you'll learn is through our lectures, I'll be going section by section just like our book does, so you can potentially follow along a lot easier than if I just kind of included random information in different spots. So in section 2.1, we're going to learn about different kinds of data. So when we talk about statistics, we want to know that we're going to be looking at a lot of different questions that we want to understand and learn about using statistics. And to do that, we have to have what we call variables. Variables are going to be what we use in our studies, a characteristic that's in a study. So this is an incredibly wide definition, but we'll talk about examples of variables here in a moment. So some examples of any variable could be someone's weight, the number of crimes they've committed, their major in college, their blood pressure, their number of items sold at a store. These are all different kinds of variables or characteristics of a certain kind of study. And when it comes to variables, we have two kinds, quantitative and categorical. Quantitative means numerical, or it represents some kind of number. So for example, up here, weight and number of crimes would be quantitative variables. However, it gets a little bit more complicated because quantitative variables can be broken into two types, discrete and continuous. Discrete quantitative variables represent a variable that has a set number, or it's a number that isn't any kind of decimal or fraction. So for example, number of crimes committed. Someone can't really commit 2.3 crimes, right? So that would be discrete. Or the number of children someone has. No one has 3.7 children. So that would be discrete because people only have 1, 2, 3, 4, 5 children, or they commit 2 crimes, 10 crimes, 20 crimes, etc. However, we also have continuous quantitative variables, and these are variables that has a range of possible values, which includes fractions and decimals. So, one example on our slide here would be weight. Weight can range from, for example, 120 pounds to 130 pounds, with every number in between. Someone can weigh 135.6 pounds, another person can weigh 200.7 pounds. Right? So that is a continuous quantitative variable. So again, we have quantitative, which represents a number, but then we also have categorical. And categorical variables can be understood as an observation that belongs to a set of categories. So again, look at categorical and think categories or groups. An example on our slide would be college major, right? Because I think most of us are criminal justice majors in this class, while some of you may be nursing students or business students, sociology students. So that would be a categorical variable. Another example would be the type of pet you have or the type of cell phone you have. And I want to stress that this is incredibly important when moving on in this class. So we need to understand the two different kinds of variables and how to distinguish between the two. And now that we understand what variables are, we also have to understand that variables have what we call a distribution. And the distribution of a variable describes how the observations fall or are distributed across possible values. So for example, we see four different shapes here. And we're going to get into those with a bit more detail soon. But just look at these shapes here, right? These are different kinds of distributions. So if we were thinking of weight, for example, this would mean that a lot of people probably are somewhere in the middle of that weight range, whatever that weight range is. This says that it's constant or steady. This would indicate that we have more observations on this side, and this would indicate that we have more observations on this side. It's a very, very basic understanding, but we'll talk more about that in the next couple sections. Lastly, in this section, we want to talk about frequency tables, and this is an example of a frequency table. And what frequency tables do is they give us values for the variables and tell us exactly how many observations we have for each variable. So this first column here is degree. High school, bachelor's, MBA, master's, law, or PhD out of a sample of 40 people. We see that 2 have only a high school degree, 7 have a bachelor's, 20 have an MBA, 3 with a master's, 4 with law, and 4 with a PhD. This basic set right here is technically a frequency table. However, when we talk about frequency tables in this class, we're going to also use what we call relative frequencies. And all that is a relative frequency just takes the number in that cell, so 2, and divides it by the total number of people and gives us the decimal of 0.05 or 5%. So you'll see that 17.5% have a bachelor's degree, 50% have an MBA, and so on. And that's a frequency table. Again, that's a very basic understanding, but we will actually talk about frequency tables much more in this class later on. So I want to move on to section 2.2, which if you're following along is on page 32 of our textbook. And we're going to talk about different kinds of summaries of data. First, we're going to talk about how we can use graphs to summarize categorical variables. And if you recall, categorical variables include characteristics that belong to a set of categories. Okay? So we could use a pie chart, for example, showing us the amount of people that have different kinds of pets. And we see that the largest number of people that have pets belongs to the fish category. We could also use a bar graph. This is for the number of people, number of voters that prefer these cereals here, Corn Flakes, Cheerios, Life, and Kix. And we see that most people, or a majority of the people, prefer Life cereal, with the second most common cereal being Corn Flakes. Okay, so we can use pie charts, or we can use bar graphs. For quantitative variables, again, these are variables that represent numbers, we use what we call histograms. This might look a lot like a bar graph, but what we see is that the bars are clustered together, so they're pushed close together. And this enables us to draw a distribution over it to give us an idea of the shape of the distribution. So this histogram essentially shows us that the most common gross monthly salary is just over $1,000. Okay? And then we see a couple people having $1,500 out here, but a majority of people have less than $1,000. And that's a histogram. And these will become really important in this class overall. So let's talk about shape again. Because when we talk about quantitative variables and histograms, we have to talk about shape. And if you recall just a few minutes ago, I elaborated a little bit on shape back on this slide here and showed you the different kinds of shape. Well, we're going to get into more detail of what those shapes are, what terms to use when describing them, and what they mean. So first and foremost, I want us just to ignore these two here, and I want to look at the left side here. This is what we call a symmetrical distribution, because if we draw a line down the middle, it's like a mirror image. They're both the same. And what this indicates to us is that the mean, median, and mode of those observations are all the same. Okay? Again, a symmetrical distribution has a mean, median, and mode that are the same. And if you draw a line down the middle of the hump here, it's a mirror image. And in statistics, this is not often the case. However, for this class, we will often assume that this is the case for our data. Second, we have what we call a positive skewed distribution. I will be calling this a right skew distribution because the tail, and that's what we call this here, the tail pulls to the right. And actually, let me do it this way. I apologize. So the tail pulls to the right, and what this indicates is that the mean, median, and mode are all different. Specifically, I want us to learn this. The mean is to the right of the median, or it's larger than the median. So in a positively skewed, or what I want to call right skewed distribution, the mean is larger than the median. The reverse is true for a negatively skewed distribution. Here we see that the tail, again, this is the tail, we see that it pulls to the left. So we're going to call this a left skewed distribution. I'm okay if you use negative or positive, but I prefer that we use right and left. I feel like it's a lot easier to understand. So in a left skewed distribution, the tail pulls this way, which means the mean is smaller than the median. This will become very important in our homework assignments in the next several weeks. So that's the basic idea of section 2.2. Section 2.3 is going to elaborate on the idea of mean, median, and mode, and how to use it to measure the center of our quantitative or numerical data. So there are a couple ways we can describe the center of our data. One of the most common is to use the mean, which is the sum of the observations divided by the number of observations. And this is kind of like the balance point. If you think of our numbers on a teeter-totter, it would mean it kind of evens out. That's the balance point. We also have the median. The median is the middlemost value of the observations when you order them from smallest to largest. And I understand that for some of you this might be a bit elementary, but these are actually really important to understand because in statistics, sometimes the mean will be good to use, and other times the median will be better to use. And that's because sometimes the mean and median can give us different understandings or ideas about the data that might be skewed or misleading. Some of you might be thinking ahead and saying, well, what about outliers, Kaylin? What about them? Specifically, outliers are the numbers or observations that fall far outside the bulk of the data. So think about if we had our age range of students, let's say, is 20 to 45. But then we had one student that's 75, right? That's an outlier that falls on the outside of our range of our majority of our students. Or let's say the St. Louis Blues, because they won the Stanley Cup, let's say they scored 20 points in one of their games this year. That would be an outlier because my understanding is that most hockey teams in general don't score that high in a game. So that would be an outlier. And when we have outliers, we want to use the median because the median is resistant to those outliers. Okay? So let's talk about an example. Specifically, go to page 52 and look at example 11. And what they show is they're showing us data on CO2 emissions from fossil fuel in different countries. And they show that the mean of those values is 4.6. And the median is 1.8. If we were to use the mean, what that would tell us is that the average CO2 emissions is 4.6. However, that can be really misleading because we have an outlier of 16.9, which pulls that mean up. So it'd actually be more accurate to say, well, we have a median CO2 emission of 1.8. Okay? Next, we have what we call the mode. And the mode is the value that occurs most frequently. And it describes a typical observation in terms of the most common outcome. Oftentimes we use the mode to describe the category of a categorical variable that has the highest frequency or highest number of votes or participants in that group. So mean and median are great for quantitative, but are not great for categorical. This is where mode comes into play. Mode is actually really great to use for categorical variables. You'll notice though that we can use mode for quantitative variables, but it's only really most useful when we look at discrete variables that look at small numbers. So for example, our book uses example 6 in that chapter, and the mode is 2 hours of daily watching. But again, the mode is not always useful for quantitative variables, so we should always consider using mean, median, or mode. And that's the end of 2.3. Easy peasy. So we're going to move on to 2.4. And 2.4 is going to start elaborating on what some of you might consider some more difficult concepts. So when we talked about shape or spread of our data and the distributions, we talked about looking at the center of the data and how it pulls one way or the other. In section 4, we're going to start talking about how we measure the variability within quantitative data. So first of all, we want to understand how the range can help us understand the variability. So measuring the center using mean, median, or mode is simply not enough. We also want to understand the range. So for example, we see in our book on page 58 a little graph in yearly income for the US and for Denmark in thousands of dollars. The range for Denmark is only about 35 to 45,000. However, the range for the US is 20 to 60. It's a very wide range. So if we only looked at the mean, median, or mode, it would be harder to understand why Denmark is higher than the US. Another way to measure variability, though, is what we call the standard deviation. This is incredibly important to understand. So if you do not get this concept, especially or any of the material we've talked about so far, please connect with other students or with me because we have to understand these small building blocks before we can move on. So we also have the standard deviation, which takes all of our data into consideration, including the smallest value and the highest value, whether it's an outlier or not. And what the standard deviation does is it acts as like a measurement or a unit of measurement. So in essence, it describes the distance of how far a piece of data or an observation falls from the mean. Again, the standard deviation is a unit of measurement in which it describes the distance of how far an observation falls from the mean of that data. To calculate our standard deviation, we have a lot of confusing looking jargon here if you're not familiar. So we're going to go over this piece by piece, okay? So S stands for standard deviation. We're going to be using this a lot and these symbols a lot, so make sure you're paying attention. So the standard deviation is calculated by taking the square root of the sum, this is sigma, that means sum, of x, which is your observation, your solo observation, minus x bar, which is the mean of all of the observations. And we square it. And we divide that by the number of observations minus 1. So again, to go over that, standard deviation, or S, is equal to the square root of the sum, or adding up, one observation minus the mean squared over the number of observations minus 1. Okay, and we'll go through an example here shortly. But first I want to talk about what standard deviations mean and how we can interpret them. So if we have a standard deviation that is positive, that means that it falls above the mean or to the right of the mean. If we have a negative deviation, that means it falls below or to the left of the mean. And sometimes we're going to talk about variance. And what variance is is if we were to take our standard deviation and square it, which you can do very easily on your calculator. And the larger, this is really important, the larger the deviation, the greater the variability. In other words, if the standard deviation is, say, 10.2, we might imagine our distribution being really spread out. Whereas a standard deviation of 0.5 means the data is not as spread out. So let's start to understand what standard deviation is by working through an example in our book. If you have the text with you, this is going to be example 12 on page 60. And we're just going to start by reading the information, okay? So example 12 on page 60 is what we're looking at. Picture this scenario. Students in a class were asked on a questionnaire at the beginning of the course, how many children do you think is ideal for a family? The observations are classified by student's gender, okay? So men, we had 7 observations for men. So I'm just going to start typing out some information that might be important. So we had 7 men. And how many women did we have? 7 women. Okay? So men said 0, 0, 0, 2, 4, 4, and 4. So that is each observation, each person. One person said, 3 people said 0, 1 said 2, and 3 said 4. Okay. For women, 1 woman said 0 kids, 5 women said 2, and 1 woman said 4. Okay? So, we want to explore the following question. Both men and women have a mean of 2 and a range of 4. Do the distribution of data have the same amount of variability around the mean? Okay, so we're going to tackle this piece by piece. So first I want to figure out how did they get that mean and that range, okay? So to find the mean, we're going to add all of these observations up, which gives us 18, 12, 14, I'm sorry. That gives us 14, divided by the number of observations, which is 7, and that gives us 2, okay? What is the range? Our lowest number is 0, and our highest number is 4. So 4 minus 0 equals 4. That's how they got that, okay? The women, same thing. We add that up. We get 14 divided by 7 equal to 2. And the range, the highest number is 4, and the lowest number is 0, giving us a range of 4. So same mean and same range, okay? But do the distributions match for men and women? If not, which distribution has more variability? So now, we're going to start calculating. So I want to go over the men first. And I'm actually going to show you because some of you might actually be doing homework in Word, and that is perfectly acceptable if you are or you are not. Just make sure you're doing the same steps. So we're going to create a table of 3 columns and 7 rows. So we're going to look at our value, which is x. We're going to look at the deviation using our mean. And then we're going to look at the the variance. So we have our first observation is 0. And how did they get that data? Zeus. Okay, so we have a table here, and I'm just going to type in our values here. So 0, 0, 0, 2, 4, 4, and 4. Okay. And we're just going to calculate the variation, or excuse me, the deviation for each observation. So to do that, and again, think of our PowerPoint here. To do that, we're just going to take the observation minus the mean. So we're going to take 0 minus our mean, which was 2. Okay? And that gives us negative 2. We're just going to do this for all of them. Okay, so 0 minus 2, same thing, equals negative 2. 0 minus 2 is negative 2. So again, all I'm doing is I'm just taking the observation, which here is 2, minus the mean, which was 2, and that gives us 0 for that deviation there. And we're doing the same for the others. So the observation 4 minus the mean, which is 2, that gives us 2. And it's the same for the next two observations. Then what we're going to do to find the variance is simply square these numbers that we got. And what that means is you're just taking the number and multiplying it by itself. So negative 2 times negative 2 gives us a positive 4. Again, we get a 4 and a 4. 0 times 0 is 0. 2 times 2 is 4. 2 times 2 is 4. And 2 times 2 is 4. Okay? So that's for the men. Well, what about the women? Let's do the exact same thing. So we have our value, which is x. We have our deviation and our variance. So I'm just going to type out our values here. 1 woman said 0 kids. 5 women said 2 children. And 1 said 4 children is ideal for a family. So what do we do to find the deviation? We're going to take the value that we were given, the observation, which is 0, minus the mean, which was 2, and calculate that out, negative 2. Then we have the observation of 2 minus 2, which is 0. And that's the same for the next observations. Oops, excuse me. Didn't mean to add it there. 2 minus 2 is equal to 0. 2 minus 2 is equal to 0. And again, all I'm doing is taking the observation minus the mean. 2 minus 2 is, again, 0. Then lastly, 1 woman said 4. So 4 minus 2 is 2. And we're just going to square these. So negative 2 times negative 2 is 4. 0 times 0 is 0. And 2 times 2 is 4. Okay? So all this does is this gives us the basic information we need to start calculating our standard deviation. Because remember, we have to take the sum of those values and square them. So we're going to sum the variance, and that will give us, for this group here, 4 plus 4 plus 4 plus 4 plus 4 plus 4 is 24. And to find the standard deviation, we still need to divide it by n, which was 7 minus 1. And what does that give us? We get 24 divided by 6, which then, once you work it out, is 4. Lastly, we need to square root it. So if we square root 4, we get 2. Okay? So S equals 2 for the men. Okay? And if you didn't catch that, we'll do it again for the women here. So to find the standard deviation, once we have all this information here, we're going to take the sum of the variance. And why the variance? It's because the variance is the deviation squared, right? So to get this numerator, all we have to do is add the variance, which when we add those up, that's 4 plus 4, that's 8. And then divided by 7. And what does that give us? If we pull up our calculator, we take, 7 minus 1, which ends up being 8 divided by 6. If you use your calculator or your head, you'll see that 8 divided by 6 is 1.33. But we still haven't square rooted that yet. So if we square root that number, we get S is equal to 1.155 for the women. Okay, and remember, the standard deviation can act as a unit of measurement. So what this indicates is that the distance between any observation and the mean on average for men is 2. By contrast, when we look at the standard deviation for women, it's 1.155. Because 2 is greater than 1.155, we can say that the men have greater variability in their viewpoints about the number of children for an ideal family. Okay? And that's standard deviation. If you don't understand it, please ask. I'll be happy to work it through with you. It is very important that we understand standard deviation before we move on to any other chapters. So now, one of the last things I want to talk about is the empirical rule. And what this is it teaches us how to better understand the magnitude of the standard deviation and what it really means. So what we see here is a symmetrical distribution, right? When we draw a line down it, it's like a mirror image. And what we see here are these lines on each side. And this little symbol here, it's like a little O with a tail. That stands for standard deviation. That's one way we symbolize standard deviation in statistics. So we have positive 1 standard deviation, 2 standard deviations, and 3 standard deviations on each side. Positive on the right, negative on the left. And what we know is if we were to draw an invisible line up here from negative 1 standard deviations to positive 1 standard deviations, the empirical rule tells us that 68% of any observations in a standard normal curve or a symmetrical distribution, 68% of those observations will fall within 1 standard deviation of the mean, negative and positive. For 2 standard deviations on each side, that covers 95% of our data. So a lot of our data is covered by 2 standard deviations on each side. Even more so, we see that 3 standard deviations towards the right and towards the left covers 99.7% of observations, or nearly all of them. Okay? So when we look at a bell-shaped distribution or a standard normal curve for a large data set, typically we see most observations only falling within 3 standard deviations of the mean on each side. It's very rare that we see standard deviations way out here. But when the distribution is skewed, right skewed or left skewed, the most extreme observation may not be nearly that far from the mean. And you can see that on page 64. Lastly, let's talk about some terminology that's very important in this class. Our book is going to start talking a lot about sample statistics and population parameters, and some of your homework will ask you to differentiate between the two. So how do we tell the difference? Here's my trick. If we know that something is a sample of a larger group, we know that's a sample statistic because they both start with S. If we know something is a population data, it's a parameter, a population parameter, because they both start with P. So for example, the average age of UMSL undergraduate students is 25 and a half years old. Do you think this is a sample statistic or a population parameter? If you said sample statistic, how did you come to that understanding? And for the same, if you said population parameter, why did you think that? because when we're talking about the average age of UMSL undergraduate students, that is a population parameter because we're looking at the entire group of UMSL undergraduate students. However, if I said the average age of 100 UMSL undergraduate students, that would be a sample because we're only taking a small portion of the number of undergraduate students. So again, because we're looking at all undergraduate students at UMSL, that's a population parameter because we're looking at all of them. However, if you were to go out right now and interview 100 students out on the quad, that would be a sample statistic because you're only taking a small portion or a small number of undergraduate students. So that wraps up Chapter 2. I know it might have felt like a lot, but what I want you to do is work through each of these problems here, and I've given you the pages for each problem. And you need to show your work for each question. The first question will ask you to use the internet, and I want you to show the table that you get from the internet. If you have any questions about the homework, please reach out to me. Otherwise, I will talk to you in the next video. Take care.